All right, welcome all. Second app workshop. Um, on the side, I've been experimenting more with the build parties and trying to get people just building code in public and encouraging, I think pair programming, I hadn't done a whole lot of it before, but I've been doing a lot of it this past 6 weeks basically, and I'm a huge fan. And we should be doing this for everything. This is like, like you find the hammer and everything's a nail, but uh, like as a pedagogical tool, it's so valuable to just put two people together. And then you have like an audience that knows more than you do anyway. So they're always like, mid and fab or someone's just dropping in and telling you what the right way to solve these problems are. So I'm loving it. It's fantastic. So drop in this Friday. We are going to be building, what was we going to be doing? Oh, Doppler Harbor and I are going to be implementing an RSS feed out of Duchess Tipprell's blog software. So it won't use command line stuff like we're talking about today, but it's another good one to take a look at. All right. So command lines. This is what we want to talk about. Some of you did a version of Hoon School that actually included parsing. And after I did that the first time, everyone, including Palfin, told me that I was insane for trying to put parsing in Hoon School, but I have no apologies to you. Moral fiber. So we're going to talk about command lines, and we have to know how to parse text. We have to get from text to like a value or a product or something that the Urbit system can actually work with. What do we care, right? Like, why are we worrying about command line interfaces? Well, obviously, command lines are pretty primitive part of computing, and so there's a lot of things that we do that, we associate the command line with the terminal, but there's a lot of things we do that are actually text-based user interfaces. Search engines are probably the most salient of these, and then things like game consoles and so forth. The way that chat bots and Chat GPT and these others work mid-journey in practice, they are command lines that they're trying to interpret a certain kind of input. Voice assistants, device streams are kind of functionally command lines in a way, if you start thinking of byte streams as being similar to a command line. Anyway, so there's a lot of reasons to get used to how would you actually work and manipulate a text user interface. So we have Dojo. It's rather an old piece of hardware in Urbit terms. I don't know when it was kind of brought into its modern form, but I would guess like 2017. Like it's kind of an old piece of infrastructure. It's similar to Bash. It doesn't do some of the things that we would like it to be able to do, like pipe things together. And I'm hopeful that at some point we'll be able to get a good Dojo upgrade. But it does know how to interact with different pieces of code on your system. And so this is where the convention of generators comes from, right? Like in pure Hoon, there's no such thing as a generator. Right, a generator is a Dojo convention that allows you to take a gate, provide a sample to it, and get an answer back at a command line that you can then iterate on, or you can redirect to disk or whatever you want to do. So when we build a command line agent, we're going to build it to work in a manner similar to Dojo. We're going to be typing at the prompt and just working with things directly at that prompt. We need to understand three things essentially. First, we need to understand how to parse text, how to take text as an input, and then turn it into something useful. We need to know about Shu. We actually don't need to do a lot with Shu explicitly, but Shu is a library that acts as a backbone for managing your agent sessions. So if you have multiple terminals attached or no terminal attached, whatever's going on, Shu is managing that for you. And then Sol is a library SOLE is the library that instruments the effects and the results that arise from your Shu programs. So in the tutorials that I've put together that we're going to go through today, we're going to talk about these different aspects here. We're going to talk about a little bit about how to parse text and how to build these agents, and then we're going to build a calculator agent that's going to be a reverse Polish notation calculator. So it's going to have a stack. We're going to push, two numbers on, a 1 and a 2, and then we push a less, and we get a 3 out the three were places on top of our stack there. So that's basically what we're going to build to get us starting here. Now, okay, let's go ahead and get a fake sod and work that way. Let's see, is this, yeah, that's a fake sod. All right, zoom, get off my screen. And let me get chat open for you. All right, and as usual, feel free to interrupt, ask questions, go through whatever part of this. All right, we don't need anything special in here to get started here, but the basic idea of a parser is that it is a rule to take something out of a text string and match it to some value. Typically, a parser rule, the simplest parser rules will simply return the value that they parsed. Building a full parser from scratch can get pretty complex and pretty complicated. You end up defining this whole set of intermediate rules that match particular clauses like valid commands or so forth, or types of values that can be put in, rather than building the entire parsing rule set at once. There are also a lot of parsers in Hoon that you'll be able to just work with. When we are working at the command line with parsers, we are going to use a function called scan. We're going to give it a tape, and then we're going to give it a rule. And if it is able to correctly parse the value, it will return to you a chord. We're going to do a lot of switching back and forth between chords and tapes. Sorry, just the way life is here. It will give you back a chord of the value that it is correctly parsed. So as you can see, ACE, basically anything that's one of the ASCII character names would be able to parse that single ASCII character inside of something. But a single rule won't parse other things. And so you'll get back the syntax errors that shows you where it is failing to parse forward in some particular value. We're also going to have to work with combinators. If you haven't worked with combinators before, the method of constructing them feels a little bit clunky because we're going to do a lot of gluing pipelines together with Mixig, the Mixig rune. But in practice, we're just defining some kind of rule pattern that lets us match across various rules. So it lets us, try either a sequence of rules in order, or try a set of rules in any order, just match the first rule that actually works here. So for instance, in this particular case, let me do a Mixig, and let me plug these together like this. All right. So what did this Mixig rule do for me here?
Did it try each in sequence?
Okay, so in sequence is the key part here. So plug sort of plugs one rule into the next. What does it actually return back to me? What's the type of the thing that it returns back to me?
It's a cell of the correctly parsed kind of units.
Yep. So it'll pull those components out, those tokens, I guess we'd call it in conventional parsing terminology. Unfortunately, and there are probably good deep reasons for this if we thought about it, unfortunately, it returns to you a cell and not a list. And when you start building more complicated parsers, this can lead to some interesting problems because it's not a list. So there's some assumptions that you can't make about what you're getting back out of it. So plug is going to apply every rule in order. Hose, in contrast, is going to just apply one of the rules. So let me call the, all right, so we have parsers. ASCII names are the simplest ones, and there'll be some others we'll look at in a moment. Combinators, plug, match in order, hose, match any, but only one. Okay. And so pose breaks at the first character after it matches one of the rules. So it's a little bit weird that way. Another thing we can do is we can put star in, and star will match something any number of times according to that rule. So it modifies the rule by letting you match multiple times to the rule. I guess that would be a combinator technically here. We don't use it with a mixed sig because we're not composing an arbitrary number of them together. It's always one rule. The star is applied to one rule. So in this case, now I can match any number of sigs, and these actually come back to me. It looks like these come back to me as, at least with head and tail tags. Let me see what. Let's see. So I guess I would want 6, address 6 to get that. So address 6 here. So I guess that's not actually a list. It does have an I and a T face attached to it for a head and a tail, but it's still not actually technically a list. Actually, you know what? The T, the fact that it's getting picked up like this means it's a Wayne or a list pat T, which means it actually, so star must actually be returning to me a list, is what that looks like. So let's try, see if it's happy with that. Okay, it's happy with that. All right, so star gives me back a list. Anyway, so they're not gonna be totally consistent as you go around in these. Another one, let me give you a more complicated rule here. All right, so what does just do? So you know what a pose is. Let's pick a rule out of the bag of rules. Pick the first rule that matches. So what does just do? This one's easy. Softball, come on.
This is the it'll match it exactly, right?
Yeah, so we'll give it a chord and it'll do an exact match. It's not over a field of things. I wouldn't be able to mix these, and I wouldn't even be able to like sequence these. It would like break it to try and sequence them. On the other hand, if I did a plug here, let me take out the diff at the end here. Yeah, so if I give the plug here, it'll actually break those up the same way. You'll notice, and this will be generally true, that for all of these, I'm actually getting every single character back. There's another parser called easy that will like eat a character or chomp a character and not give you any result back. Like sometimes white space you just want to throw away. There's any number of white space that matches star ace and you don't care, right? You just want to care that it's actually separated. All right. So we can put together different collections of rules like this that'll match different things. Some of these are okay. So there's a lot of complicated parts of the parser. It's a big, very organic part of hoon.hoon. And so not everything is just a name or lives in the same core. And so you might have to hunt around to find the thing that you're looking for in a particular case. So if I want a rule that will scan, something that looks like a path, there's another parser called vast that has a gash inside of it. Yeah, and so what this will actually do here is this parses it and turns it into Hoon code for me. Right, and so it actually picks up it's parsing the whole thing as a path. So it picks up the fact that there's something before the faz as a null valued entry. And then the rest of these are units that are actually evaluated components of this. So this is not only parsing it, it's parsing and evaluating it into the Hoon AST at the same time. There's all sorts of pieces all over the place. We could do the same thing with another version of this. Let's do, oh, it's limp and vast. Limp is in vast. Yeah, so this is functionally what gash vast is doing, is it's doing a more of fast limp fast. So more, what does more let us do as a combinator then? What do you infer from that?
Is it kind of more of the same parsing rule?
Yeah, it's kind of a repeat pattern in a sense, right? Like you have a rule that's a faz and a thing after it, whatever limp vast does, which looks like it matches something that's a valid sort of path shaped name and turns it into this sand stuff. Some of you may have run across this or not. You remember the sand rock stuff when we talked about atoms a very long time ago? It's worth taking an aside for real quick, just so you get used to that. I guess I want zapcom, zaptiz. Let me see what this was. Oh, null's a terrible one to choose. All right, let's do 5. All right, so sand and rock are the difference here in constant versus like variable. This has some ramifications in the type system, but that's where the sand head annotation that's showing up in these cases is, it's saying it's a pat TA, it's a term. The raw numeric value of it is 55, and then it's not a constant. It's not, it's not sen 5 or sen character 5 like that. It's actually just the value 5 in text, like just the chord 5, which is the ASCII 55. Okay, let's see. We could do, oh, another thing we can do. This is a good one to see for you. Let's do another version of this. Let me try. Let's try sim. No, sim won't do it for me. So we can get rid of, okay, where I'm going with this. Let me go back up to the one that worked here. All right, so we had this one that worked here. I don't know, like parsing is slow in general. It feels like it's being like unusually slow right now, but parsing is not fast. All right, let's try this version of it. All right, so how does this version with the plug faz in front of it differ from just the more faz by itself? Look at the difference in returned values in these two.
So this
What's it doing there?
It starts by giving you the faz in a chord, and then it continues on doing the 5 faz, 6 faz, 7 faz.
Yeah, and so from a code design standpoint, it means that we know there's a value here at the front that we're throwing away. We're not sort of hanging on to an empty entry here like it's generating for us. And then all of the values that actually match this pattern are already correctly parsed. So we're gonna do things like that. Easy do it for me. It's been a while since I've used easy. Let me see. Oh, easy must work a little bit differently than I'm recalling it. Then easy, like I said, easy eats one and throws it away. So we can, anyway, we don't have to worry about what easy's doing there. But what we would do then is we would define arms that match particular kinds of things for us. So let me give you, we could do these as lesses. Let me define these, a couple of these, so there's a command matcher And I have a path matcher that's very similar, built from what I just did. Let me give you both of those. And now what I'm able to do is try and scan something that looks like a command. Let me try Command Ace. Oh, I'm changing my gears here. Okay, let's do packs first, and then I'll take a look at a different one in a second. Okay, so this one then carries out this operation, and I'm able to parse something that looks like a command into actual values that I would be able to pass into a Hoon expression and get something useful out of. The change that I also have suggested in my notes is instead of packs, which is unitized on those values, is to use stapso, which does something very similar to the rule that we wrote right here, but it converts it to a path at the same time. So it deunitizes and makes it a path, explicitly path type. So now we, given a rule like this, then we would be able to pass it into a handler that would turn it into something useful. We are going to use a command called cook to do this. And what cook will do is it will accept a rule, accepts a gate and a rule, and whatever value comes out of that rule gets processed through the gate and then turned into like some sort of actually useful value, which is pretty neat. And we can start doing some cool things once we have that capability. So for instance, let's see, let me cook one this way. Okay, so if I were going to write a rule to, I'm just going to give it, all right, we'll call this get file. This is going to be a rule. All right, so it's going to take a gate as its first part. And I will just leave a stub in there for now. Oh, it's not going to let me do it. Oh, Dojo. Okay. And then I'm going to give it a actual parse rule at the end, which could be different shapes depending on what we're doing here. So this is going to be your pattern whenever you want to parse text, not only matching text, but you want to turn it into a useful value now. So we're going to create a command that we give this rule a path, and then it is going to immediately turn it into, it's going to do the scry out of the file. So we could say tis path dot ket. I guess we'd want to chord back sen cx, and then this only takes a path. So let's weld our current beak to that and count 1, 2, 3. Okay, I think that's correct. Let me copy that for you. We'll find out as soon as I run it on some real code here. And so now I should be able to run scan lib. Well, let's go with one that I know is here because I'm actually sure if that path is defined. Gen cat hoon. And then I'm going to give the get file rule to this and see what I get. Okay. So there we go. So now I've written a command that actually does something for me with the text that I am popping directly into scan here. So questions about this basic part of scanning? Come on. I know you've got questions. Scanning is all over the place.
Hey, Neil.
Yep.
Quick question. So let's say you're hitting an API and you're looking to scan kind of an array of values, meaning like let's say it comes back with like an account and a balance, and it's several of them. Would you DJSON with like a parser where it kind of like a do loop and stops, and it throws those matches in an array, or is there a more elegant way of doing that?
So there's more than one way you could think about handling that kind of process. If you wanted to do it purely with parsers, you can define recursive parsers. They're a little bit complicated to think through because you have to figure out exactly how you're causing it to scan down into the rules as you generate the data sets. Right now, this isn't for App Workshop, but right now I'm trying to write a general purpose XML demo parser tutorial, and actually correctly closing tags is kind of a mess when you think about like what's happening recursively. So I'm working through a particularly nasty example of that right now. There's another example that's in the notes, but basically you can build something that's a trap-like structure to apply rules over, so to parse like an arbitrary number of lines.
Yep.
But there's some handlers, like there's a gate called knee, Knee, that you have to apply to get the compiler to actually deal with this correctly. So it's a little bit thorny and it's hard to design, but you can do it. There's also the regex library that was written that, like, all of parsing is like slower than it should be because it's built on top of the base parsers. And at some point we should like really like see if we can build lightning fast parsers on top of this. But right now that hasn't been a blocking issue for us. But you can do more things with the regex library too.
Okay, thanks.
All right. There's some examples in here for parsing things. Actually, you know what? In response to your question, I do want to take a look at this code here. This is a generator that will parse an arithmetic expression. So I can type something like 1 + 5, and it will correctly turn it into the thing that you're doing, that you're trying to deal with. So this gives you an idea of what's happening when you scan something complicated like that. So you receive a tape, you're going to barket, you're going to scan the expression. All right, so you're getting math in, you're going to scan it with expression. So expression down here, you see we have to do this knee call on a trap. This siglus is an interesting one. Has anyone used siglus before? This lets you cache components. It's a signal to the runtime to cache the result of an expression calculation. They are used a lot with parsers because parsers are slow. So it's telling you, once you've calculated this, cache the result, so you don't need to calculate it again. So you're building this trap that contains the rule that's going to be deferred, but then it's going to be able to work recursively. So we're going to be able to pull term and use term, and term is looking for a multiplication component and is going to give us factor in a term. Factor uses infix combinator. This infix is between two values, so it gives you open and close parentheses. So we're going to be able to write expressions that are, let me go ahead and save this then real quick and show it to you very quickly. Zod base gen. All right, so I should be able to do expression parse like a single value should just evaluate. Something with a less, it's parsed here, and it just reduces down to, yeah, so slug is a way of applying this to the result of the thing that you're getting out of the thing after this, which is kind of complicated. But we can build this as sort of an arbitrarily recursive evaluator here. And then it's always just basically stepping in and out. But this is kind of an example of what you run into with knee. It's good to work through this example to see how it works. Deferred knee expressions are complicated enough that I have to like stop and carefully think through them every time I actually sit down to write these. But this gives you the idea of what's going on with them.
Okay, thanks.
All right, let's see. So yeah, so basically those combinators, I guess, slug applies a gate, and then there was what was the other one we had? Cook, which they're a little different from each other. Cook is kind of the more general purpose one that we're going to deal with there. Now, let's look at something with shoe. Let's see here, sod. We have an agent that does something with shoe. Where am I? Oh, I've never mounted base. Oh, I'm in Urbit Zod, not Zod. CD Zod. Now grep. Okay, so there's a base app shoe. Okay, here. All right, so when we work with shoe, it's going to manage our attached agent sessions. What's interesting about it, we're going to import the shoe library. What you're going to notice is that we're using a card that's different than card agent Gall, which is our normal card. And we are going to apply agent shoe and then have a command handler, an input parser, in this case over types, that we're going to apply to this as well. So it is also an agent modifier the way that like debug or something is as well. And what it's going to do for us is it's going to add some specific arms. So we have all the regular on arms, where it's going to add 5 arms. There's going to be a command parser arm. This is going to be an input parser. It's going to look like the work we were just doing with input parsing. There's a couple lines of boilerplate that you always have at the top, but then it's going to parse every input. It's only going to permit valid keystrokes. So this is going to give you Dojo real-time parsing. First 3 lines are always going to be the same. They're always boilerplate, except that the stag of Pam and bar, true and false. If this is true, if it's true, then as soon as you type something that evaluates to a command, that command executes. And if it's false, you can keep typing until, so you can type like a more complicated command. I think that's the right way. It's either one way or the other way on that. Tab list, we're normally just going to stub out, but it provides autocomplete options. So it's kind of neat that it actually does that, but it'll give you an idea of your autocomplete stuff if you press tab. On command is the big one. It's going to be called whenever a valid command is run. This is going to produce your actual effects coming back out. Okay. It returns quip card cab this. The difference, however, is that it's going to add in new types of cards. And so you'll look at this block right here, terrible color. We're doing a call hep of sig, and then a collab of the soul card, and then we'll tie this to whatever. Why isn't this a col cab actually? Is it a collab? Anyway, we're going to be building this soul effect, which is head tagged with soul, and then it's some sort of text effect. And there's 7 or 8 of these, from being as simple as here's just some text to doing what in this case is going to be bold green text. And then the tape as a chord is going to be the value that we're actually giving back. So this is where we're going to be able to start doing text styling now, or rewriting parts of the screen, reordering parts of the screen if we wanted to, draw dialog boxes and so forth. We're going to stick with styled text for now because 1, that's the most general case, and 2, it's a lot easier to think about than redrawing on your terminal session there. There's a can connect and an on connect and an on disconnect, and those are all connected to the bar link connection here. So those will probably basically always look the same. Des in this case is the shoe library wrapper, the same way that we do default normally for that. So can connect, on connect, on disconnect basically will always look the same unless you actually want to do something fancy like trigger some effect when they bar link to it and connect to it for the first time. All right. Yeah, let's see. I think we saw everything we care about with those 5. Yeah, okay. Now, the effect that we're getting back here, this thing here, this is going to be a head tagged piece. So for instance, what this would look like for a different message, if I were going to put all this together with cat heps so you can see the types attached to it. I should actually have another type on top here, which should be shoe effect, shoe, and it should col hep shoe, and I guess that should be marked like that. Okay. So a shoe effect is a card that you are getting back. It's a new valid card type that shoe will automatically turn into a dill card that gets processed with everything else. You don't need to worry about those details. Shoe handles that for you. It's kind of a wrapper for this. The only shoe card currently supported is a soul effect. So you're just going to head tag a soul effect with shoe to do anything with it. There are many kinds of soul effects. As I said, the most interesting is to do a color tag and then pass it a styled string, a sticks. Style text is kind of complicated and messy. And as you can see here, we have a leading cell that is the, it's like, is it blinking? Is it bold? What's going on with that? You can do underlined text, like things that are normally supported by terminals, for instance. Then you can do color. In the example up here, we were just using Senji for green. Down here, we can actually do 24-bit color, so we can specify everything in HTML hexadecimal terms. And then there's going to be a chord associated with it, and then that's going to end as this one is a list, and then it's wrapped by a list, and it's, like I say, that part gets really, really messy. I'll give you all the relevant types for you to work with, but those are a little bit complex to parse through, particularly. I have defined a couple of demo agents. Let me see if I actually have that on this fake sod already or not. Probably quickest to just go down and find it. Let me show you what this agent does first. Okay, sorry. I know where this is. I do have a fake sod that has this sod in it, but it was in the other agent because I moved it. Okay. All right, so what track 7 is going to do, it's going to let me type any letter, and it's just going to fill an 80 character wide, randomly colored string of that letter. So it's a great demo for just how does colored styled text work in Hoon? Like, how do we actually build this in a in any sort of a straightforward way? Oops, Control X. So bar link links an agent for the first time. Once you've bar installed it, if you want to actually interact with the command line agent at the command line, you bar link, and that's when the on can connect is checked and then on connect is used. I'm already linked, so it doesn't tell me anything special here. And then you're able to do Control X to switch to that in and out of that. Now, what I would like to look at is track 7. All right, so this is all boilerplate. Instead of naming it des, which I felt was kind of confusing, the shoe default I named leather because of shoe leather. And it's the same number of letters as default, so it works well in that case. You'll notice that this call agent does nothing. Has no state, it has no pokes, it doesn't do anything. But the command parser and the on command are going to be the interesting parts for us. So let's go back up to, sorry. All right, so we have okay, so any command is a pat T. So I define a general command as just anything that is a chord. And so the command parser here, what it's going to do is it's going to accept that, and it's going to stag PAM, which means as soon as any valid input is received, it's going to kick it over to on command. And then the rule that I'm using here is boss 256 more gone, I guess, hit, however we want to say that. Exactly what that's doing. In this case, that ends up being kind of a complicated way of saying I can type any character. This is what matches text that's basically valid UTF-8 text inside of the Hoon parser there. I don't remember what gone does offhand. More means I can type any number of them, which actually would give me different options if I change this. So right now, if I type any character, it immediately gets evaluated. And this PAM is why that happens, right? Like it immediately gives me the output. If I change that to a bar, then I would be able to type something longer, and it would get, I'd be able to type whole words and have those display as well. Boss 256 means that we're going to cap it at full bytes. This is often used to exclude command characters where you're like setting up a range of valid characters from 32 to 255. So it's boss is kind of convention that we're going to run into occasionally, but I don't think it's really necessary in this case. I could probably just say QIT here, stag PAM QIT, and get the same effect out of this command. All right, on command is doing the work for us here in this case. Just going to return clip card this, colcab this, cathep list card. All right, what's complicated about this one is, okay, it's building a shoe effect like we saw a moment ago. Let me scroll back to this on the bottom so you can see what the card actually looks like. Building a shoe effect. It's building a soul effect. So head tagged shoe, head tagged soul, head tagged color, KLR. Then I'm asserting type sticks, so it's styled text. And then what I'm actually doing here is I'm building a random color string with the entropy input and outputting this value here, this sticks value here on command on the value that I actually receive is the thing that gets generated and then welded together as a list. And then this is what kicks back out as my list of cards at the end. So because it's building these, it's a little bit more complicated. And this is why we have this trap inside of the card builder there. But track 7 does one thing, and that one thing is receive any text input and then process it. All right, so if we want to build a, let's see, 245, we're in good shape here. Any questions about track 7 before we take a look at the calculator agent that we're going to build? I could probably do more sophisticated things, like instead of just specifying 80 characters wide, I could query, I could scry into Dill and find out what my current terminal width is so that it's always doing it to whatever my current terminal width is, for instance. But gives you the idea here.
Yeah, I'm curious about this cat hap. So like the shoe effect, cat hap and the soul, are those like, they almost look like they're in the wrong place. Like, shouldn't they be above the like the toss of soul, the terms?
Well, okay, so the card is shoe, is head tagged with shoe. Let me see if I have an example of what a full. Okay, so this would be, for instance, we're gonna see this in the code that we're gonna look at in a minute with the other. This would be a full expression there, and then I'm cripping, so I could even simplify this to. All right. So this, let's see, that's a full sig, colas. All right, so the shoe effect is everything from this point onwards. And the only kind of shoe effect is a head tagged soul effect. So everything to the right of this is a soul effect. So soul is the head tag, and then it's a soul effect after it. And then this is an example of a sticks. No. Then the soul effect, this particular soul effect has a color head tag, and then this is a sticks inside of it. The sticks is a list of either more complicated things like we saw up here, but the simplest sticks is also just a pat T. So a sticks can be a list of pat T or a pair of style and sticks. Does that make sense?
Yeah.
It's, like I say, this is really messy, and so cantankerous. I pushed 2 new tutorials to the app workbook as a result of writing this lesson, just to try and clarify for myself what's actually going on with these. Now, my dirty secret about writing these things is that whenever I write Hoon code, especially if I'm doing anything like weird and complicated like this sort of stuff, I assume that I am never going to be able to remember how I got to the point where I'm at. And so like I'm always like writing a tutorial on the side to get to the point where I'm at, because I'm assuming that I'm going to lose track the next time I look at this, because sometimes you get complicated like this. The upshot of this is that we are getting a lot of tutorials out of me never being able to remember how to build these things in practice. So, all right. Any other questions about shoe soul stuff here before we look at the library that we're going to build? This is all in the lesson notes in a complete form. So let's see. Let me go to, let me share a different window here. All right, so this is the reverse Polish notation calculator. I'll mess with the zoom in a second here. All right, so this is an agent that we'll be able to use. What it's going to let us do is, well, actually, I have one installed. Why don't I just show you that first? This is the stack-based reverse Polish one that I was mentioning a moment ago. Okay. All right, so what this means is I can type a value and do math on it. And it will always consume the last two values on the stack if it's a binary operator. And I think every operator we have in here is a binary operator, except there's a dot, which is just sig-ham the result here. Show the result. So we can do minus, we can do divided. You know, we have the basic arithmetic ones. One of the possible challenge exercises for this is to implement modulus, which it actually won't even let me type right now. I think I can do, there's tar. I thought I had exponentiation in here in some form too. No, I guess I didn't implement that. I don't have a power in here. Oh, I don't have a power in here because the only version of floating point exponentiation that's out there is the one in Saloon, which isn't generally available yet unless you want to go install it. That's why. Okay, that's why I didn't implement it. All right. Anyway, so that's what this calculator does. We give it commands, and then we're able to process it down to particular values. So let's pop over to GitHub and look at the code. So this is in RPN. All right. We're going to start with the structure file because that's always a great place to start. All right. So we're going to define operations. These are going to be head tagged as ops. And the reason I'm doing this explicitly is it lets me filter on atoms versus cells on my stack, because what I actually do is I process everything, I push it on the stack, and then if it's a cell, I take it off the stack, and then I find the operation and I operate on the next two things in the stack. And if it's an atom, then I just push it on the stack. I don't do anything else with it. So I'm defining an alias for a number, which is a pat rs. So this should be a single precision floating point value. And then a command is either a num or an op. I guess I should have said num since I went ahead and defined it there, but whatever, it's fine. I have a library. Okay, this is where our parsing is going to take place. All right. So look at these entries here. All right. So we're going to cook a gate against a rule. So for instance, lus. What we're going to do is if something is correctly parsed by lus, then we are checking, although it's not formally necessary because only lus would be parsed by lus. We're checking that the value is lus. And if the value is less, then we're passing back head tagged op senad. And we're doing that for each of my operations here. There's another one dot that was having trouble because of the way I think because I was this one wasn't parsing correctly. So I think I ripped it out in the version that I have in the notes. It wasn't breaking anything, but it wasn't processing to show them all, to sig-ham them all. Anyway, and then what I'm doing is I'm posing all of them together. This is what we're going to use in command parser inside of our app in a moment. We're going to use ops to actually parse values. So these are all of our ops parsers. Our num parser is done as Royal RS col SO. So this parses a numeric value into a floating point value. However, you'll notice that I was just typing things like 3.5. I wasn't doing .3, .5. So Royal RS is actually invoked after the dot is parsed off the front inside of the parsing tree. So in this case, it has the convenience that I'm able to type something the way a normal person would type a decimal value. I could type 9.5, 3.1415, and it would just work for me. So I'm using Royal RS for this. All right, process. This is kind of the big one, the big magical one that's doing a lot of junk for us here. So what process is doing is it receives a stack, which is a list of commands. Okay, so remember that a command is either a number or a value, and it's going to return something that's the same shape back out. We're going to add a sig bar in case something breaks. So sig bar are error logging messages. They will only show up in case of failure, but they'll show up in your stack trace so you can figure out what's gone on. If my stack is empty, then I should crash because I shouldn't have an empty stack, right? Like, I could have an empty stack, I guess, when I start this for the first time, but if I have entered any command, I no longer have an empty stack. And then I do a switch over my possible ops. So I'm going to flop the stack so I can grab the last thing on it. I'm doing a lot of flopping back and forth as I work with this because of the structure of stacks, because it's easier to grab the head off a stack than it is the tail in time. If it's an op add, then I get my augend and my addend, and I actually carry out the operation using the add col RS, right? If I were to add .1 and .2, it would not give me .3 because those are floating point values. They're weird things as block numbers, and the regular add arm will not work on them correctly. It will not yield what I expect. So I have to use add col RS, sub col RS, and so forth. So I do this for addition, subtraction, multiplication, and division. If it's show, then I print the top value of the stack, and then I return whatever's left after I take that value out. You'll notice that in every case, I'm doing this weird flop slag stuff because I'm just trying to flip it and then chop off the end and then flip that back around and return that. So that's how I'm getting rid of the values. Snag 0 would be the actual operator, the operation that I'm doing. Snag 1 and snag 2 would be the next two values. And if one of those fails, then I'll get failure processing operation on stack. And then if it's not any of these, then it is a pat RS, and I just return the stack. So if the last thing on my stack is a number, great, fine. I don't need to do anything. I just return this value. All right. Yeah, nothing special with marks. So let's look at the actual app implementation now and see what's going on. Other than defining a stack here, it's going to be pretty similar to track 7. So I'm importing RPN as lib. The reason I'm doing this is because I'm also importing RPN as a structure file. So I'm renaming it just so I don't run into trouble if I need to refer to both of them here. So there's my stack. No pokes, peeks, anything like that. All right, my command parser. See what's going on with my command parser. So my command parser, I'm going to cook my command handler from the library, the thing we just looked at, with numlib and opslib. So this is going to be my parser for values and for operations. And then whenever I press enter, only when I press enter, not when I type a single character that matches, when I press enter, then on command will run. So on command gets those values. You'll notice that it does get other information like which session I'm talking about. I'm actually, most of the time I ignore that unless I want to actually explicitly manage sessions. This could probably be made a little bit more efficient, but I'm welding my command onto my stack, and then I'm processing it into the new stack. And then as a convention, I'm producing two shoe cards to print those values for me. So that's the one with the arrow here. That's where the output is actually coming from in all cases except dot. So I could also echo my input. I'm not doing that here, but I could echo my input as well. So you'll notice that I'm choosing, this is where I'm choosing to do bold. It's nominally green, but it's whatever passes for green in the terminal color scheme operations that you've done as well. And yeah, everything else is boilerplate. Nothing else special in anything that's gone on here. All right. Now, let's go back to Teams. Okay. All right, so if I type something, so I can 7.5, whatever. So I could do minus, I get this value. I'm in a meeting right now. If I try to do an operation, it'll let me type it here. Parser's happy with it, but when I try to evaluate it, then it'll fail. And as part of my stack, I get that value there. And it actually dumps the stack back out. You can imagine doing a better pretty printer or something to handle that, but that's what actually generates my value there that lets me figure out what is the thing that went wrong. And then I get the regular stack trace to deal with everything else. One of the side effects of this is that it unlinks. So I still have track 7, but I lost, as I control X, I lost RPN. So I'd have to relink RPN to do this. So now I have track 7 RPN in Dojo. So, all right. There's a lot of ways we could expand this. We could add a modulus or a power. We could change it to operate on a different kind of values like pat RD, double precision floating point. We could extend it to support named values, right? Like I'd be able to say like, I can't type it here now, but if I go back to Dojo, I could, A = 5, something like that. I ought to be able to do that. I could implement it as really a proper stack. Right now, it's kind of a poor man's stack. It's not really a stack. I'm just treating it as such. So, there's a lot of ways I could modify this that would be fairly straightforward changes to make from what I have. And so that's kind of in your hands, right, to go figure that out. I'm also going to link to you in the lesson notes from this, Halfon's TUI Toys demo branch of Urbit that contains the slide and snake and some of the other tools that he built to demonstrate things at the Volcano Summit. So there's some very cool things in there that are kind of the next level up from anything that we looked at in this lesson today, but we'll give you an idea that there's a lot more you can do at the terminal command line interface once you get used to building and working with these kinds of conventions here. So, all right, ¿qué más? If there are no other questions, then we'll go ahead and wrap, but that's what I've got for today.